In this video, we're going to be looking at the zeros of a polynomial function. So we're going to tell not only from the equation, but also graphically how we actually find out the zeros of a function. So as an example, we're going to start with our equations. We're going to find the zeros of each function, identify each as being a real zero or complex zero. So first thing we want to do is figure out what the degree of this polynomial actually is. So when I'm looking at a question like this, x plus 2 times x squared minus 5x plus 6, my degree is going to be told to me by basically this first term right here has a degree of 1, and the first term here has a degree of 2. I'm looking at those because those are the highest degree terms in each of the parentheses. If I were to multiply those together, I would get 3. So my degree on this one would be 3. So I'm expecting to get 3 answers. Depending on what they are, I'm going to classify those based on whether they're, real numbers or whether they're complex numbers. Now, the way to do this with ones that are in parentheses like this without an exponent is essentially I'm just going to take that x plus 2 and I'm going to set that equal to 0. So that's going to give me one of my zeros would be -2. And I know that one is going to be a real number. There's no imaginary root on it at all. The more complicated one is that one that has the quadratic part. And essentially what I'm going to do is I'm going to first figure out if it's factorable, and if it's not, then I'm going to use the quadratic formula to do that. Now, on our last video, we talked about how we can quickly do that using the discriminant, so I'm still going to do the same thing. I'm going to find b squared minus 4ac. So if I take -5 and square it, minus 4, a is 1, and c would be 6. So I'm going to multiply those together, follow my order of operations, and see what I end up with. And that'll tell me a little bit about what's left. So I've got 25, and this will become -24, which gives me 1. So I might have readily seen that that was factorable. If I didn't, then that discriminant would tell me that it should be factorable because I have a perfect square or a 0 for my discriminant. So this one's factorable. I'm looking for, because I've got nothing in front of x squared, looking for numbers that multiply to 6 but add up to -5. And so that would be -3 and -2. So I'm going to factor this chunk here, x minus 3 and x minus 2. So my next step then, because it is factorable, I'm going to just take those factors and set them equal to 0 and solve. And I'm going to save you the work here because I think we've already done that many times. This would be x equals 3 and x equals 2. And again, those are also going to be real roots. On model 2, again, degree of 3, I've got an x squared times x. So when I have x plus 3 and solve that, I'm going to get x equals -3. X squared minus x minus 1. I'm not easily seeing that that's factorable, and I'm suspecting that it's not. But I am going to find the discriminant anyway. So take b squared minus 4 times a, which is 1, times c, which is -1. So I'm going to have 1, and then this will become plus 4, which gives me 5. But because it's 5, it's a positive number, so I know I'm going to get real answers, but they're certainly not going to be nice factorable ones. So I will have irrational roots, but not complex roots. And again, the way I would know that they were complex is if I had a negative value for my discriminant, and I'm not seeing that happening here. So my solution then, I'm going to use the quadratic formula. I'm going to take the opposite of b, so the opposite of -1 is 1, plus or minus the square root. The discriminant is 5, which I've already calculated, so I can just plop that in. And then 2 times 1 is 2. So again, because I don't have any imaginary components, no square root of negative numbers, these are considered real. It appears we only have 2 roots, but this is 1, and these actually contribute 2 more. One of my roots is 1 plus the root 5 over 2, and the other one is 1 minus root 5, all divided by 2. So keep that in mind, that the degree tells us how many overall roots we're going to have. Real numbers plus complex numbers, complex roots. Some graphs. And graphs, I think, in a lot of ways, it's a little different approach. There's less calculation and more visualization. Here they're telling us a little bit of information about the graph before we get too far. That it's a cubic polynomial. And so if something's cubic, I know then it has a degree of 3. So that's the first thing that they're asking us for. Again, the degree tells us how many roots it's going to have, complex and real together. Here we can get a little bit more fine-tuned and talk about positive versus negative zeros. So the zeros are basically where the graph is going to cross the x-axis. And so here I've got two values in the positive area that the graph crosses the x-axis. So I'm going to call those positive zeros. And again, both cross over. But I also have this other one over here, a negative 0. And so together, positive zeros and negative zeros, they're real. I don't know exactly what number they are, but they're real numbers. There's 3 of those. Now, if my degree is 3, then I've taken care of all my roots. The complex numbers are effectively going to be the ones that are left over that we can't account for based on the graph. So there's 0 complex roots. In this 5th degree polynomial, first thing I'm noticing is I'm not seeing it cross 5 times. On the previous one, we saw it cross 3 times, once, twice, third. That was a degree of 3. I would expect from a graph a 5th degree polynomial to have it cross 5 times, and I'm not seeing that happen. So first things first, degree is definitely 5. My positive zeros, I've got only 1. And my negative 0, this is where it gets a little bit strange. I've got 1, but it doesn't cross over. And that is typical of what's called a double root. Technically multiplicity, but we're not going to get beyond double roots. We're not going to talk about triple or quadruple roots or anything like that. So for our purposes, we're really looking at double roots. They've got kind of an uncharacteristic, probably, I guess, uncharacteristic crossing. It doesn't actually cross. So the number of negative zeros technically is 1, but we're going to call that a double root. So essentially it counts for 2. Now, we said that the degree is the total number of real and complex zeros altogether. So I'm looking at here, and because I've got 1 positive and technically two negative zeros, that's only going to give me 3. And so what I have to have left then is the complex roots. So because I've got 3 here, I'm going to have 2 complex zeros left over. Nice, easy way for you to check. Complex zeros always come in pairs. They never come individually. So keep that in mind. What's characteristic of a complex graph or a graph with complex roots is there'll be usually some kind of bend somewhere along the way. And just looking at that graph, it seems like right about here, there's kind of a weird bend that I really wasn't anticipating from my original graph. And that would be indicative of where the complex zeros affect the shape of the graph. All right, let's do another one here. This is called a quartic polynomial. And again, a quartic polynomial will be a degree of 4. And so on this one, when I'm looking at the zeros, I'm seeing that it does cross twice, or it does hit the x-axis twice. One of them crosses over, so that's a single root, versus the one that just touches it and bounces, that is a double root. So I'm going to put there's 2 positive zeros, one of them being a double. And then negative zeros, I'm seeing 1 over there. And so again, thinking about what we've actually got here, 4th degree, I've got 1, 2, 3, 4. I've taken care of all of my degrees, so then my complex zeros would be 0. There's none of them. All right, let's do this last one here. This is a quadratic function. So quadratic functions we typically expect are going to have 2 real numbers for the zeros. It doesn't always happen. So a quadratic function will be a degree of 2. And looking at the graph, it doesn't look like it has a positive 0 or a negative 0. So the only other possibility then is that all of our roots are complex. So I'm just making this one up, but it could be something like our answer is x equals, 2 plus or minus square root of 5i over 4, something to that effect. That's something that we're looking at. We have complex zeros. So again, the number of positive zeros and negative zeros and complex zeros has to add up to the degree of the polynomial.